so I guess the rectangular unit vectors. Questions to hear? All right, let's make it more difficult. I may as well stick with the same number. So 5 microcoulombs, -3 microcoulombs, .4 meters between them, 0.3 meters between them. Go ahead and make that right angle. And let's make this 6 microcoulombs. And a question like this would be, what is the force on, and then pick a charge. Let's make it on this guy right here. What is the force on the 6 microcoulomb charge? The force on the 6 is the force on the 6 from the 5 plus the force on the 6 from the 3. I know it's -3, but in terms of subscripts, I'm not going to bother writing the negative. Let's think through part of this. What is the direction on the 6 microcoulomb charge because of the -3 microcoulomb charge? All right, seen a couple of hand gestures. Not rude ones, thank you. So that is the direction of the force on 6 from 3. What is the direction on the 6 microcoulomb charge from the 5 microcoulomb charge? I got one gesture there. 2, 3. Got a groundswell of 3. I assume everyone else is just laying back and being cool. They are like charges, so it repels. So this would be the force on 6 from the 5. So we're adding vectors. So let's find the magnitude. This magnitude, oh, I don't need that magnitude. This magnitude right here, so this is 9 times 10 to the 9th, times 3 times 10 to the -6th, times 6 times 10 to the -6th, divided by 0.3 squared. What it is. Yes. And the other one while we're here. 1.8 newtons. Anyone else got that? I got a nod. You got that? All right. So I know the magnitude is 1.8 newtons. We need to decide, are we going to add this using rectangular coordinates or polar?
Rectangular, you would use sine and cosine, right?
Yeah.
Rectangular.
Okay. All right, so let's establish a coordinate system here. So I hat to the right and j hat up because I lack imagination. And so this, So this is gonna be something I hat plus something j hat, plus the second one right here, which is negative 1.8 newtons j hat. I thought through the direction, I know it's down, and so that's why I dropped the minus sign here, because the minus sign is gonna tell me a direction here, and I know what the direction is. It's being pulled towards it. All right, so the other one. So 9 times 10 to the 9th times 5 times 10 to the negative 6th times 6 times 10 to the negative 6th divided by what? What is the distance between them?
This is the I hat J hat direction.
It is 0.5. We need to be able to get the magnitude first before we break it up. So over 0.5 squared.
Why is our second terminal value 6 and not -3?
Wait, why is this 6 and not -3?
Yes.
Because I'm looking at the total force acting on this one
Oh,
from here.
Thank you.
Let's see. So it's basically multiplying those 4s and 20, 120. Newtons. Anybody get that? Yeah. All right. So it's 1.8 newtons in that direction, so we do need to break it up. Now, it's a 3, 4, 5 triangle, but we actually don't need to find the angle itself because it's going to be, so if this angle here is theta, this is going to be 1.08 newtons times the cosine of theta, and this is 1.08 newtons times the sine of theta. We could find theta, that's not a problem, but we don't have to because the cosine of theta is the opposite, is the adjacent over the hypotenuse, in other words, 4/5. So this is 0.8, and this is 0.6. Or you could find theta and then take the cosine of it and the sine of it, which is legitimate. You might end up with a rounding difference there somewhere. 4. And I'm not opposed to having made a Carroll's error, but at least the process is right, if the numbers are not.
We're allowed to leave the answer that way, in that format.
Yeah, if I don't specify, then that's perfectly legitimate. I hat, J hat have to be defined. Do not automatically assume I hat, J hat. Questions? All right, so this is the basic gist of problems that deal with point charges. If I had, let me change the problem slightly. Instead of a point charge here, I have a sphere, a conducting sphere. Radius of the sphere is 0.3 meters, and it's centered 0.4 meters from the negative. I'm writing it as small as possible here. So it's now a sphere, radius of the sphere, 0.3 meters, center, 0.4 meters from the negative 3 microcoulomb charge, and 0.5 meters from the 6 microcoulomb charge. In other words, the center of the sphere is exactly where the point charge was. Now, how does the problem change?
Would you like split it up between the charge, the point particle in the center and its radius, and then from the radius to the other one, the 6th one? So you're breaking it up into 2 steps.
No. One thing that we really haven't gotten to yet, all the charge, assume I said it was a conductor, so all the charge would actually be on the surface. There is no charge in the middle.
So then that means it would be 0.3 meters closer.
Or is it
Because the center is
farther away also? Parts closer and parts farther away. We actually did the derivation of this with the gravitational force in the first semester course.
Kepler's law.
Pardon?
Was it Kepler's law?
No, it was same chapter, but not Kepler. Outside charge with spherical symmetry. If we are outside a charge with spherical symmetry, we can treat the charge as a point charge in the middle. It's a point charge in the middle of the sphere. I could have also made it an insulator with even uniform distribution. We'd still maintain the spherical symmetry, so if we're outside of it, we would treat it as a point charge. This does not actually change the problem whatsoever. If I made the radius of the sphere, 0.6 meters, well, then it does change.
And that's just because of the quantity of charge?
Now, it deals with, if you work through the math, basically, part of this is closer to it, and part of it's farther away from it. If you, it balances out, so it sort of averages in the middle. I was thinking about doing the derivation of it again, because I know how much, at least those who have seen me do it in class, the derivation with gravitational force, just absolutely loved working through, a full board worth of math, bringing in laws of sines, law of cosine, some good stuff to end up with a very simple answer. And I thought, nah, you can do that on your own, as if you hadn't been doing it already. I am going to do some other derivations though. If you're inside, if it is a conducting sphere, all the excess charge will be on the outside. We'll justify that later. So if it's inside, the force on it would be 0. So if this thing encompassed, it doesn't really matter where the center is, just so long as if the 6 microcoulomb charge is inside this sphere, then there'd be no force coming from here. Questions up to here before we actually do some calculus?
As far as the math, that's 9 times 10 to the, I can see the number.
9. 9 times 10 to the 9th.
Nine, okay.
Has
Oh,
to
yeah,
be,
because of the K, right?
Yes, yes.
which one, electrostatic or,
Coulomb's constant,
Coulomb.
or electrostatic constant.
they're both the same?
I treat them interchangeably.
Okay. I didn't know if they, I don't know the history on it.
No, there's another constant that shows up, called permittivity of free space,
Right.
which is
Okay.
related to K.
Well, it's also related to the spark, right? As far as, it's the, how you calculate at what distance a certain charge will jump out, given like the density of air and the humidity.
Yeah, then you start getting into the dielectric strength of the material,
Okay,
which does relate to the permittivity.
okay.
All right, now suppose we have a distribution of charge. There's some generic steps to take. First off, draw the picture. Sorry, I don't have a word to describe this. So draw a picture. Whether it's in your head, preferably on the paper. Create a coordinate system. I guess designate. Probably should be a verb there. Create. Define. There we go. I like that word better. Define the coordinate system. Create charge differential. In other words, dq. Create temporary variables. Because you're given a problem with certain variables in it, you'll be generally told a charge or a length or something like that, but usually when you're actually solving from scratch, you need an angle needs to be in there. Things that ultimately will disappear, but you need to define them. And we'll definitely be going through an example here. Plug into formula, Coulomb's law formula. Get it into single variable. You've got count 3, not necessarily going to do that, but. And then do calculus. Now I do this, and again, there's no nice acronym here. I do this just so that there is a commonality to solving a lot of these problems here. So let's take a look at the infinite line of charge. With some density of, charge density of lambda, uniform charge density. I have some point here, which I will call Q1, that is a distance r away from the line. And I want to find what is the force on charge Q1. So force on Q1. So go through the steps. I've already drawn the picture. Coordinate system. Rectangular coordinate system works nicely here. Let's go ahead and make this I hat and, let's make down J hat. And I'm gonna call this the x-axis, just because we're gonna need a variable at some point. All right, create the charge differential. So what we're gonna do is we don't do the whole line at once, we just look at a small part of it. So I'm gonna take this small little part right here and call that dq. So I'm looking at the force on Q1 from dq to start with, and then we'll integrate over the whole line. Now, as a general rule, when you are creating a differential, I've given you no information about whether this is a positive charge or negative charge, either of them, we don't know. But as far as doing the solution, assume everything's positive, unless you're told otherwise, assume everything's positive, and then if it happens to be negative, well, then a negative sign pops in when you put in the charge value.
It's amazing how that works with statics too.
Yeah. So I know that this will be forced in that direction. Extend that line that way. The temporary variables, well, I have big R here, but I know that in my formula, I have that little r squared in the denominator, so that is the distance between the charges, so I've got my little r there. This distance right here is x. If this is my origin right here, if this is 0, 0, this would be the point negative x, 0. And I guess this therefore would be the point 0, negative r.
No, your coordinate system was down as positive, sorry.
Thank you very much. That's what happens when I try to do something different. Now we plug into the formula. Now we are dealing with a differential here. So when I do plug into Coulomb's law, I technically don't plug into the force, I plug into the differential of the force. Is equal to K Q1 dq over r squared. This angle here is theta. That would be cosine theta I hat plus sine theta j hat. Because the magnitude of the force is right here in my fraction, but then I break it up into components of the horizontal and vertical components. Questions to hear?
That's the charge differential.
And that's the charge differential right there, dq. Now, ultimately, I can think through what is the direction of the what's the final direction of the force acting on Q1? When all is said and done, when we've gone through all the math, what would you expect the direction of the force on Q1 to be from the entire line?
With respect to the coordinate system or what?
Yeah.
Okay, so southeast. Southeast.
No. Why southeast?
We have flipped our coordinates, but just in that general direction, I would assume that the force.
That's the direction of the force from that. I'm talking about the entire line. If we did all the DQs for the entire line, I got a couple people pointing downward. Because for every point over here, I've got one over here that's pointing that way. So all of the horizontal components are going to cancel out. In other words, we can go through and show it, but I know that the I hat direction is going to end up being 0. So argument by symmetry, I'm not going to worry about this. I'm not claiming that cosine of theta I hat is 0 in doing the math. I'm claiming that in the end, we're going to end up with a 0 there, and so I don't care about it. But feel free to go through the math. You will end up with 0 in the end. And there's certain satisfaction will come out with a very simple answer after doing a lot of calculus. And a frustration of, why didn't I see that beforehand? So ultimately what I'm working with here is that my force is the integral kq1 dq over r squared sine theta j hat. We're doing some calculus here, integral, so let's bring the constants out front. K is a constant, Q1's a constant, and J hat's a constant. And we're left with dq over r squared sine theta. Oops, already have the J hat. There's a math problem. I got 3 variables in it. So we need to get it into a single variable. We don't have to use law of sines, law of cosines. All right, so charge density. What is charge density anyway? I guess I should throw uniform linear charge density. What's linear density?
The mass divided by the length.
Okay, so what do you think linear charge density is?
The magnitude of the electrical charge divided by the distance.
Or your length. So it's going to be equal to Q over L if I had a finite length, but I have an infinite length, so dQ over dL. Or in our case right here, since I have an X there, dQ dx. It's uniform, so no matter where I take my little piece of it, the charge density is the same. So from this, I know that dQ is equal to lambda dx. So I'm going to plug that in. R squared, again, this is R here, and that's X. I know that it's a right triangle. R squared is equal to X squared plus big R squared. So I'm going to plug in that for R squared. And sine theta is the opposite divided by the hypotenuse. And so sine of theta is big R over little r. So I'm going to do that substitution first. KQ1 j hat integral of, let's say I can do lambda dx over r squared times x over r. So KQ1 j hat, lambda's constant, so I pull that one out. X dx over r cubed. Well, I know what r squared is, and so this becomes KQ1.
I have a question.
Yes,
What
ma'am.
did X over R? That's R. I think it's big R over R.
Just because I wrote it there? Thank you. So that actually pops out, so that's a constant. Sure I'm going down the right path on this one, yeah. Thank you, I would have caught that at some point. I'd like to think. R j hat integral of dx over x squared plus big R squared to the 3/2. I now have a single variable.
Did you already integrate that?
I haven't integrated anything yet. All I've done is get it in terms of a single variable.
Why was the 3/2? Okay.
Because it's r cubed, I know r squared is this.
Thank you.
Okay. So I have a single variable I can put in my limits of integration. What are the limits of integration?
We said infinity, so.
Negative.
So we are at that last stage of do the calculus. sitting lonely over here, so it's been neglected enough to be dark. So my force on Q1 is KQ1 lambda R J hat times the integral from negative infinity to infinity of dx over x squared plus r squared to the 3 halves, just rewriting what is written over there. So how do you do this integral?
Negative infinity to 0 plus 0 to positive infinity. Then you take the limit.
Wait, so what day is it again?
Negative infinity to 0, and then you do 0 to positive infinity. So you break it up into 2 integrals and then take the limit.
Yeah, but you're still left. How do you do the integral though? I mean, if I did it, so it sounded like what you were saying is do the integral from 0 to infinity of that, and the integral from negative infinity to 0.
Mm-hmm.
But we're still left with an integral of this.
Property, replace it, take the derivative, but
Say it again?
I'll have to look it up. I vaguely remember it from Calc 3.
Is it the U substitution?
What would u equal?
X squared plus R squared?
No, because when you take the derivative, you'll still have an r that you'd have an x still.
Oh.
If you let u equal this, then du would be 2x dx, and I don't have a spare x floating around. There's 2 major ways of solving this. One's the math way, and the other one's the physics way.
Which was easiest?
Physics.
The physics way.
Which
Because
is
the math
two.
people have already done the hard work. Trig substitution, by the way. That you would let x equal arc tan theta, and then you'll end up with a secant, which ends up with a cosine, and or you look it up. It turns out the integral dx of, that's not the one I want. There we go. C squared plus or minus x squared to the nth power is 1 over 2 c squared n minus 1 times x over c squared plus or minus x squared to the n minus 1 plus